She was playing.
She was Into the Wild.
Joan Jett?
In that.
Yeah.
She was in Into the Wild, too.
Oh, I never saw that.
That's where I got my first taste of how one-dimensional she is.
Graduation. Oh, actually, what they told me. I'm like, come on, get somebody uses the
Looks up with her.
yeah, okay.
It looks really good on the screen. So.
On where?
For the recording and the people
Yeah, I was
watching
gonna say.
online.
This is the most deliberate.
Oh, okay. Well, for those people, when I go like this,
The loudspeaker said
Twilight the Huntsman.
Oh.
Oh God, no, no, I never seen. No, no,
oh,
no,
okay,
not
so-
going there.
Just as soon as 50 Shades, right?
It's really funny though. That's sad, but funny.
Great. Yeah.
well, no one wanted to be here at 8 in the morning.
I get it.
Captured twice actively.
trying to sound good. Alright, so welcome everyone. We're going to go ahead and get started. This is the Tools and Technology Seminar Series for anyone who is unsure about that. There's a sign-in sheet going around. Please fill that in. I do want to mention, make a comment about next week. So in the email I sent out about this week's talk, you might have noticed that it said next week's is canceled. However, it's been uncanceled. The original speaker had to cancel, but Wanfan Guan will actually be giving next week's presentation. So there is a talk next week.
Don't play with our emotions like that much.
I know, I'm sorry. But you get your pizza now next week too, so everyone should be happy. Anyway, I'm pleased to present today's speaker, Johann Gagnon-Bartsch, and he is an assistant professor in statistics.
Thank you. So I'm going to be talking today about the RUV package. RUV stands for Remove Unwanted Variation. It's tools to remove batch effects and other unwanted variation. Just as a heads up, everything that's in the talk today is on Docker. So if you go to this URL, you can get all of the code that I use and also even these slides. In fact, I'm running all of this from within Docker at the moment. Okay, so outline. I'm going to start off by giving an example data set to motivate everything that I'm going to say. I'm then going to make some high-level comments on normalization, and then also make some somewhat high-level comments about the RUV framework. And then I'll get into discussing the actual RUV package, and at the end I'll do a couple examples with the Shiny app. Okay, so to motivate everything, I've got an example data set. This is a microarray data set from several years ago, in which the goal of the study was to do a differential expression analysis to find genes differentially expressed between men and women in the brain. Study design, there were 5 men, 5 women. Tissues were taken from each of these 10 people post-mortem. 1 tissue sample from each person from the anterior cingulate cortex, 1 from the dorsolateral prefrontal cortex, and 1 from the cerebellum. So for a total of 30 tissue samples, 3 from each of the 10 people. And then each of these 30 tissue samples, 1 aliquot was sent to each of 3 labs, Davis, Irvine, and Michigan. So we end up at the end of the day with 90 microarrays, 3 arrays for each of 30 tissue samples. And so the screen is a little bit off here, but I've got down here that for each of these 90, they were assayed by microarray, and we have data on 12,600 genes. Okay. Back up. So I'm going to just show you the data. Here I've loaded in this data set into R, type ls, and here's what's inside. we've got a data frame with information on the genes, a data set with a data frame with information on the samples, and then we have two versions of the expression data. Here I've got in the comments. One is the raw data, which is to say that it's been summarized by RMA, but without the quantile normalization or background correction steps. And then I also have the more standard normalized version, which has been background corrected and quantile normalized. Okay, so here, just so you can see it, there's the data. I've got rows are the microarrays and columns are the genes. And inside, here's the data frame of the sample information. Again, rows for the different microarrays. And then I've got information on which of the 10 patients it was, their gender, which brain region it was, which lab it was assayed at, and then also chip version. That there were 2 different versions of the microarray that they used. Gene information, I've got information on all of the genes. I've got the symbol, the chromosome, and these things I'll talk more about as the talk goes on, but this is whether or not it's a housekeeping gene. This is not whether or not it's a spike in control. This is whether or not it's positive control. Again, I'll come back to all of this. Here I load the RUV package and set a couple graphical parameters. And then here, yeah, we can see that okay. Okay, here I've got a PC plot of the data. And I have it colored by brain region. So the 3 colors are the 3 different brain regions. And then the plot symbol I've got for the laboratory. And what should strike you when you look at this is that by far the strongest signal in the data is the lab effect. So you have all of the Michigan data here, all of the Irvine data here, all of the Davis data up here. So again, this is the data that has already been quantile normalized. So it's been pre-processed in some sense, but still far and away the largest signal in the data is the lab effect. And getting rid of this sort of stuff, that's going to be the focus of this talk. One other slide I want to show you real quick. So one thing that is sometimes done in situations like this is people will just remove the first couple of principal components when it looks like the first couple of principal components are a technical effect. Here I've done that. I've removed the first 5 principal components.
Did you look at the different versions of chips also, how they distributed in there?
Yes. And to a large extent, although not exactly, it's, if I remember right, Michigan uses chip version 1 and the other labs.
Oh, different places were using. Okay,
Yeah.
so there's 2 things. It's lab plus the chip.
Yeah, well, there's many things. But,
Okay.
Yeah. What was it? Oh, yeah. So sometimes you might just want to remove the first couple of principal components. What you see here is you have more or less removed the lab effect, but there's also no biology remaining either. You don't see clustering by brain region. So this is just to flag the point that a normalization can be too strong, and you can throw out the biology that you're interested in along with technical effects if you're not careful. And then as a preview, here is data that here's a normalized version that I'll get to later in the talk that's been normalized using one of the RUV approaches. And here we see that the batch effects are gone, and we also have a nice clustering by brain region. So we've got all of the cerebellum here and all of the cortex.
How did you get rid of the batch effect?
That's the point of the talk.
Yeah.
I'll show you.
Oh,
Yeah.
somehow I didn't.
This is just a preview to keep your attention. Okay, so before I get into the details, I want to make some high level comments on normalization. The first comment I want to make is that, and at least in my view, there is no one right normalization. And what I'm not saying by this is I'm not saying just that there's no one right normalization algorithm, although I think that's true also. I'm making an even stronger statement that even for a given data set, there is one no right normalization. And the reason I say that is because the normalization that you're going to do, it's going to depend on what variation is wanted, or in other words, what variation is of interest to you, and what variation is unwanted. And that will depend on your context. It will also depend somewhat on the goal of your downstream analysis. But I would just want to highlight this one. If for no other reason, the normalization that you want to do will depend on what variation you're interested in and what variation you're not interested in. So elaborating on that point a little bit, I'm going to distinguish between wanted and unwanted variation. And our observed data is going to be composed of both variation from many sources. There's going to be a bunch of variation that's unwanted, that's just technical effects, so things like the lab or the batch, variation due to quality of the reagents, due to RNA degradation, even things like composition of the atmosphere, and I could go on and on with a long list here. But then there's going to be sources of variation of interest also. Gender for sure in this example, that was the original goal of the study. And then I've got a brain region with a question mark next to it, meaning that, oh, this is a brain region may or may not be of interest. If all you're interested in is a differential expression with respect to gender, you might think of brain region as a nuisance variable. But in other contexts, it might very well be what you're interested in. So here, again, I'm just highlighting that what variation is wanted and unwanted is going to depend on the context. And the normalization will want to reflect that. Saying that again here, should we think of brain region as wanted or unwanted? I'm going to argue that it depends, and that the normalization should reflect that. I should point out that this is not an entirely trivial thing that I'm saying, because you could imagine a counter argument, someone saying that when we normalize, what we really want to do is we want to remove anything that is a technical artifact, and we want to preserve all biology. So brain region would be biology, and we'd want to keep it. And if I'm not interested in brain region, well, okay, I'll adjust for that in the downstream analysis. So that is reasonable, but I'll say that well, I'll make 2 points. One being that some biology is nearly always unwanted. So, for example, any sort of changes in your gene expression because you just ate or just exercised or anything like that. Changes due to circadian rhythm. Unless you're specifically studying circadian rhythm, that's probably something that you want to normalize away. But even more than that, and this is, I think, what is really critical, is that a lot of these biological factors that you might want to adjust for are unknown. They're unknown, or you don't have information on them, and so it won't be possible to explicitly account for them in the downstream analysis. And so we do want to try and adjust for them at the normalization stage. Okay. So elaborating a little bit more on this idea of unknown sources of variation, just highlighting it again, very often the unwanted variation comes from sources that are unknown. This is true of both technical and biological unwanted variation. And identifying and then removing this unwanted variation is especially challenging. So I'm going to say just a couple words about identifiability here. Imagine in this simple case, we're just going to say our observed variation, it's just going to be the sum of wanted variation and unwanted variation. And I'm going to make the point here on the next slide, not at all surprising, but I think still worth stating, that different patterns of wanted and unwanted variation can produce the same observed variation. So I have that in a picture here. I've got that our observed variation, it's the sum of wanted variation and unwanted variation. And I've got 2 different examples here where the observed variation is the same in both of these examples, but the part that's wanted is different between these 2, and the part that is unwanted is different between these 2, but they add up to the same. Okay. Now, if we could look and we could see within this observed data what part was wanted and what part was unwanted, well, then we'd be good. But we can't. We only see the sum here. So again, nothing surprising in what I'm saying. But I point this out explicitly just to highlight the fact that any normalization we're going to do, it is going to require some sort of extra information. Because without at least some sort of extra piece of information, we're not able to distinguish between these 2 cases. So again, nothing too surprising, but it's still worth stating that any normalization we're going to do is going to require some sort of extra information. And here's examples of things that you might use. So you might use, for example, an assumption that the marginal distribution is the same for all microarrays. That's something that you that might justify doing a quantile normalization, for example. You might have information on what the unwanted factors are. So you might have information on the batches, for example. You might know what your factor of interest is. That will make it a little bit easier when you go to, for example, do a regression. You might have various sparsity assumptions. You might have various independence assumptions. But again, you need something. Okay. One special case I want to highlight is when you do have a known factor of interest, which is the case when you're doing a differential expression analysis. Even if you have a known factor of interest, you do still have identifiability issues. The key problem is that if you don't know what the unwanted variation is, you don't know whether the unwanted variation and the variation of interest are correlated. And depending on whether or not they're correlated and to what extent, that can very much change the analysis that you do. So let me just show this picture one more time. It's a little bit hard to tell from the screen, but I made these matrices in such a way that the wanted variation in both cases, the factor of interest is the same. There are 6 rows in one group and 6 rows in another group. So you can kind of see here you've got off, off, on, off, on. So you can think of these as treatment and control, for example. And you'll notice that the factor of interest is the same in both. So basically control, control, treated, control, treated, control, treated, and so on. What differs between the 2, though, is how each gene is affected. So for example, in this lower matrix, these 2 genes aren't affected by the factor of interest at all, whereas in this one, they are. So just knowing the factor of interest alone isn't enough to solve the identifiability issue. And again, the critical issue is that the wanted variation and the unwanted variation could be correlated. Okay, so just to highlight the challenges, the 2 that I've more or less focused on in these last couple of comments are that these are related but subtly distinct. We need to worry about defining unwanted variation. So in any context, we need some way to define what variation is of interest to us and which variation is not. And then aside from just, in some sense, defining what variation is wanted and unwanted, we need some way statistically of identifying it. Okay, and so those are 2 of our key challenges. In addition, I haven't elaborated on these too much, but once we've defined and identified our unwanted variation, we still need some sort of statistical method for actually separating them out. And at the end of the day, we also need methods to validate our analysis. I'm not going to go into too much detail on those, but just thought I'd flag it. Okay. So now I'm going to just talk a little bit about, in general, the RUV framework, which will help give us ways to deal with all of these problems. Quick mini outline for the next couple of minutes. I'm going to first present a model that is common to all of the RUV methods. I'm then going to talk about negative controls, which are one of the key tools that the RUV methods make use of. The negative controls help us both define and identify unwanted variation. Sometimes, or actually always, in addition to the negative controls, we still need at least a little bit more information to fully identify the unwanted variation. And there's various different ways we can do that. I refer to these as secondary identifying assumptions. And the one that I'm going to focus on quite a bit is replicates. So in the RUV framework, two things that you make a lot of use make a lot of use out of are negative controls and replicates. So I'll explain what these are and how they're used. And then I'll just conclude with a slide explaining why I think this is useful. Okay, so here's the model. This is a model that will be used for all of the RUV methods. It's that we've got our observed expression data y. It's going to be equal to some wanted variation, which is the product of a factor of interest and some regression coefficients, plus unwanted variation, the W alpha, which again is unwanted factors and regression coefficients, plus some random error. And then I've got in this table here, the y is the observed data, m is the number of observations. In this case, it's 84. I lied a little bit at the beginning of the talk. I said that there were 90 microarrays. 6 of them, for whatever reason, are missing from GEO. So it's actually 84 that we have. There's 12,600 genes. X is the factor of interest, which might be something like gender or brain region. W are the unwanted factors. And then very importantly, this W, typically, it's unobserved. We don't know it. But it consists of things like reagent quality. Okay. And just to point it out, this model is originally due to Leek and Story and to Stagel in 2007 and 2008. Okay, so now negative controls. Negative controls, and these are central to all of the methods I'm going to describe. They are features, by which I mean typically genes, that are unaffected by the factor of interest. So in our case, unaffected by gender, for example, but are affected by the unwanted factors. Okay. So as an example, one example might be spike-in controls in a lot of microarray experiments, this one included. A researcher will spike in bacterial RNA, and then there's some of the probes on the microarray that respond to this bacterial RNA. It's spiked in at fixed known quantities, and typically this is used as a quality check. I'm going to be using it as the basis of a normalization. Basically, the logic is going to be that the spike-in controls, any observed variation in the spike-in controls is not going to be due to gender, because it's this external spike-in, but it will hopefully pick up a lot of these unwanted factors. And so that'll form the basis of our adjustment. To be a little bit more explicit, so suppose that we have a number n sub c of our n columns of y, our negative controls. We're going to let y sub c be the m by n sub c submatrix of y that contains only the columns of the negative controls. We're also going to define this beta sub c, alpha sub c, and epsilon sub c similarly. These are all submatrices. And we then have this equation. It's the same model, but just applied now to just the negative controls. Now, what's important here is that this beta sub c, that's equal to 0 by assumption. That is our assumption that the negative controls are unaffected by the factor of interest. So that term disappears, And we're left with what looks like just an ordinary factor analysis model. And so we can actually estimate W by factor analysis. And that is what essentially solves our identifiability problem. The negative controls give us a way to estimate the W even for when the unknown or when the sources of unwanted variation are unknown to us. Okay, so I want to stop and just talk for a second about this negative control assumption. So this is our key assumption. It's this assumption that the negative controls are unaffected by our factor of interest. And what I really want to point out is that this has to be some sort of assumption based on prior knowledge. The negative controls cannot be discovered de novo from our data. And in particular, what this assumption does not mean, or what we cannot do, is we cannot just look at our data, find genes that are uncorrelated with our factor of interest, and call them negative controls. We can't do that because it's actually possible that the negative controls are things that are correlated with the factor of interest, and that would happen if the unwanted factors are themselves correlated with the factor of interest, then the negative controls should be also. Okay, so this assumption is not an assumption about correlatedness of the negative controls with the factor of interest. This is an assumption about whether this might be slightly too strong of a word, but I'll use it because it's helpful. It's an assumption about whether or not the factor of interest actually causes changes in the negative controls. This is saying that the unwanted factor does not have any effect on the negative controls. Okay. And I also want to point out when I'm talking about the negative controls, they don't need to be perfect. So it is a seemingly strong assumption that we need to pick genes or spike-ins or something like that are unaffected by the factor of interest. But they don't need to be perfect, and in a lot of cases, having a set of genes that at least most of them are unaffected by the factor of interest will do, or in some situations, depending on exactly which method we're using, it will even work if, on average, they're unaffected by the factor of interest. Okay, so it's a somewhat strong assumption, but also it's not one that needs to be perfect. Okay, so that's the negative controls. I'm now going to talk about secondary identifying assumptions. So I said that we need the negative controls, but then we also need something else. So we saw that the negative controls, they help us get W, but we still need to get alpha somehow or other. And here are some ways that we can do that. One is to have a known factor of interest. So if we're doing a differential expression analysis and we've got negative controls, we're pretty much good to go. In some cases, though, we won't have a known factor of interest, which that might sound kind of weird. Like, what kind of analysis are we doing if we don't have a known factor of interest? What I mean by that is something, for example, like if we're doing a clustering analysis, where the biology of interest is these clusters that we are discovering, but they're not known ahead of time. So in situations where we don't have a known factor of interest, other things that we can do, we can make use of an assumption that the factor of interest and the unwanted factors are uncorrelated. And that might be justified, for example, if we've got a randomized study where the factor of interest is treatment or control and was assigned at random. Another thing that we can make use of is if we have gene-wise covariates. This is something that I'm not going to talk very much about in this talk, so I'm going to skip over that. The one thing that I'm going to talk about a lot, though, is we might have replicates. And replicates are another way of getting alpha. Okay, so I'm going to talk about replicates now. So suppose that we have two replicates, y1 and y2. And so what I mean by this would be, for example, that say both y1 and y2 they're both microarrays from the same sample. So say patient 1 cerebellum, but one of them was done at Irvine and one of them was done at Michigan, for example. So we have 2 replicates. This is an expression for or from the model for one of them, and then we've got also for the second one. And then critically, this part here down at the bottom, this is key. The factor of interest in both of them is going to be the same because, again, both of these come from the same tissue sample. So the biology is going to be the same in both.
But it's not a replication of the same experiment since it's done in a different place.
Same tissue sample, and then they had different aliquots and sent them off to the different labs. So the biology should be the same because it's come from the same tissue sample.
Not a technical replica.
It's a biological replica.
You've got different people, like lab techs can have an amazing effect on how these things work.
Shipping, travel, everything.
Oh yeah, sure.
And it was different chip versions between some of the sites, and that can have a big effect.
But in both cases, it comes from the same tissue sample extractor. So whatever biology that you're going to be interested in, that factor is going to be the same.
It started the same.
Yes. Well, that's the point. The biological factor, the thing that you're interested in, that is not varying from one to the other. Okay, so if we subtract these two, replicates, there's the math of it, but then critically, this x2 minus x1, so whatever the biology is, that's going to cancel out. This term will disappear, and we'll be left with this. So we're now left with just the unwanted variation. So again, this is the same tissue sample was sent to 2 different labs, and what I'm saying here is that any variation that exists between what one lab says and what the other lab says is essentially, by definition, stuff that's unwanted. In an ideal world, the 2 labs would say the same thing. Okay. And so if we now have a bunch of replicates, we could build up a matrix of these differences and do factor analysis, and that would give us a way of identifying this alpha. So just to highlight here, what I've said about negative controls and replicates, they're similar in a lot of ways. You can think of them as dual to each other. The negative controls, these are genes where we assume that the beta is 0, and they allow identification of the W. And then conversely, replicates, these are array differences, and where in taking the difference, the X is 0, and this allows us identification of alpha. So between the 2 of those, we're able to get both W and alpha and identify the unwanted variation and then remove it. Okay, so just to highlight why I think all of this is useful. Why do we want to try and remove unwanted variation using negative controls and replicates? One reason is because this general framework is somewhat flexible, in that by that I mean that the negative controls and the replicates, they not only help us identify the unwanted variation, but when we go to choose what is a negative control and when we go to choose what is a replicate, and I guess I should say for a second, there are different notions of replicates. There's technical replicates, there's biological replicates. When we choose what we mean by a replicate, we are implicitly also defining what variation is wanted and what variation is unwanted. And I'll make this a little bit more explicit when I give some examples in a little bit. But in any case, again, by choosing negative controls and choosing our replicates, we're not only identifying the unwanted variation, but we're also defining it at the same time. So that is helpful to us.
How often do you have data set that has such kind of biological replicates?
Well, it depends a little bit on what you mean by by biological replicates.
So you said you need the replicas.
Mhm.
So I see that technical replicas is quite often, but you want biological replica that is that I'm not sure how often you can see that.
Well, I'll say often enough, and I'll also say that you do not very often see experiments like this one that I've showed where everything is replicated, or in this case triplicated. That is pretty rare, but it is not that uncommon to find experiments where at least a handful of the samples are replicated, and even just having a couple of them can often be good enough.
Think about it. So if they can do biological replicates, that means they have the resource to do everything on the set with the same technical conditions. Then why do they bother to do the biological replicates in the first place? So say they can, so they have the same brain tissue that want to send to different labs. Then why don't they do everything in the same lab?
Let's can I talk about that at the end?
Yeah.
Okay, cool. Because I still have quite a bit that I want to get through. But yeah, let's talk about that at the end. Okay, so why I think this is good? It's flexible. It's also transparent. Like I said, whenever you do some sort of normalization, you're going to be relying on something to get the normalization going. And by doing everything in terms of negative controls and replicates, the assumptions are really front and center, which I think is good because it makes it easy to debate them. People can discuss whether or not it makes sense. And then, as I hope I'll show in the next couple of slides, also it seems to work well. Okay, so that is all the high level comments that I'm going to make. I'm now going to go through the details of actually using the RUB package. Like I said, all of this is on Docker. So at some points I might skip over fairly quickly in the interest of time. But a quick mini outline of what's included here in the discussion of the package. I'll just give a quick overview of the functions that are included in the RUB package. Broadly speaking, there's going to be methods for regression analysis, or which is to say differential expression analysis, and then also methods for global adjustments. So I'll talk about those separately. And then once I do, we'll move on to the case studies with the Shiny app. Okay, so quick overview of the functions. There's basically, so here are the core RUB adjustment methods. There's 2 for global adjustments, RUB1 and RUB3, and there's 4 for regression or differential expression. I'm going to talk about these separately in a minute. So these are the main adjustment algorithms. There's some helper functions to help use these. The ones that I have highlighted here in yellow, these are ones that you'll use on a pretty regular basis. There are some functions for making nice plots, and there's also a couple functions that they're exposed to the user, but not actually intended to be used on a regular basis. There are some cases where they might be useful, but on a regular basis, probably not. And the one that I really want to draw your attention to is this one, getK, which I've highlighted in red. This is a function that returns a number k, which is the number of factors that you might want to adjust for. I want to point out that this function should not be relied upon. At best, it will occasionally be useful for an RUB4 analysis, but in general, it's not something that you want to rely on. And then there is also the Shiny app. Okay, so I'm gonna start off by talking about the regression methods. they all have a fairly similar format. They take as input a Y, an X, and a control. RUV2 and 4 also take a tuning parameter K. There's an optional Z matrix, an optional eta matrix, and for RUV R inverse, there is an optional lambda parameter. So let me just explain what these are. The Y is the expression data. That is that's going to be an M by N matrix, so observations by genes. X is your factor of interest. Control, that's an index of the negative controls. Z is any other covariates that you might want to include in the analysis. Eta is gene-wise covariates that you might want to include in the analysis. And then there's K, which is number of factors to adjust for, and lambda, which is a ridge parameter. I'm going to go through each of these quickly, but individually. So again, Y is the expression data. It's arrays by genes. You'll, at least for microarray data, you'll want the data to be log transformed. But interestingly enough, other than log transforming, it's often best not to do any further preprocessing. So things like quantile normalization. The reason for that is that in a lot of cases, if there's quite a bit of variation between different biological groups, the quantile normalization can introduce more warping than itself. X is the factor of interest, so things like gender of A region. If you do not want to include an intercept in X, and just as a rule of thumb, the fewer factors that you include, the better. And the basic reason for that is the more stuff you put into X, the less can be estimated and adjusted for in our estimated W. And if you do have several factors of interest, in general, it's going to be best to just rerun the analysis several times, one for each factor that you're interested in. Z is any additional covariates that you want to include. Things like if you have a known batch, stuff like that. If you want to include an intercept, which generally you do, and that's the default, Z is the place to put it. And then, like with X, just as a rule of thumb, the less stuff you put into Z, the better. So actually, in most cases, I would recommend just not having anything in Z other than the intercept. Again, the reason is the more you put in Z, the fewer dimensions you have available to include in your estimated W. And elaborating on that point slightly, so even if you have, for example, known batches, and there's variation, or there's differences between the batches, it's typically not the case that batch per se is causing is the source of the unwanted variation. It's things like differences in the reagents, various technical differences that differ between the batches. And so I guess what I'm saying here is that the batches are at best a proxy for the actual unwanted variation. And letting the algorithm estimate that unwanted variation rather than including it yourself often performs better. There's one very notable exception to this, which is that if you have a covariate that affects only a very small number of genes, and specifically the same genes that you might expect to be affected by your factor of interest, then you might want to explicitly include this factor in your Z, because since it affects only a small number of genes, it might not get picked up in the factor analysis. So just to be a little bit more explicit, an example would be if your factor of interest is a disease that affects only a small number of genes, and then the covariate that you want to adjust for is a drug that also affects similar genes. So for example, a lot of the people that have the disease might be taking a specific drug. in which case you'd want to adjust for that explicitly with your Z matrix. Okay, eta, I'll skip over that. The controls, these are very critical to success. You want your negative controls to be unaffected by the factor of interest. You want them to be affected by the unwanted factors. And ideally, you'd also have it that they're somewhat representative of the other genes, meaning they have similar ranges of expression, not affected by their own unwanted factors. That is, to some extent, a reference to spike-ins. Spike-ins have a lot of their own noise just due to their own administration. And as I've said already, these are not things that you can discover from the data. It needs to be based on prior knowledge. And but that said, they don't need to be perfect. K, that is number of factors to adjust for. It's for use only with RUV2 and 4. And it's useful to use this specifically when you are concerned that your negative controls might contain at least some biology. In that case, keeping K small will help reduce the risk of over-adjusting.
Sorry, what do you mean by your negative controls may contain biology?
Meaning that if, for example, you're not using spike-in, but you're using something like housekeeping genes. Yeah. And this is partly why I say that you want to choose K by hand and not use this get K function. Here's a quick comparison of the regression methods. Their various strengths and weaknesses. I'm going to skip over this. You can look at it on online, but I'll just point out that RUV-R inverse is a good compromise of features that's useful as a good default. A quick technical note. So the different methods make use of the negative controls in slightly different ways. The RUV2, you actually do need the negative controls for them to be unaffected by the factor of interest, whereas you have a weaker condition for the other methods. Okay, so now I'm going to give an example analysis. Here I've gotten the code. I'm going to run the RUV-R inverse function. I'm going to pass it my data matrix Y, that my factor of interest is gender, and I'm going to say that my negative controls are the spikes. That'll return a fit. I'm going to then put the fit into this RUV summary function. And the RUV summary function, it takes, in addition to the fit, it takes, again, the original data matrix, the data frame with the sample information, the data frame with the gene information, and then what that returns is this nice summary of, it's got, for example, p-values from an f-test. If, in this case, I only have one factor of interest, so the p-values for the individual factor, there's only one, and that's going to be equivalent to the f-test, but when you've got more than one factor, it'll give you the p-values for them individually, along with a bunch of other information. Okay, push forward. There are a bunch of plots that you can make then just by taking this this fit summary and plotting them. Here we've got a p-value histogram. This is more or less what you want to see. If once unwanted variation has been adjusted for, the p-values should have more or less a uniform distribution, except for the ones that are significant, the ones that are truly differentially expressed, and for those you get a spike right at 0. So this is looking good. There's also a function to make an empirical CDF if you don't want to look at a histogram. You can do a power transform on that, so you can, this is basically allows us to see that there's that spike there. Using various ggplot things. Here I've got, for example, the different ECDFs for the spike-in controls, for the housekeeping, and so on. I'm going to skip through these plots. Well, there's one other one. This I want to highlight is an important way to be able to validate your analysis and know if you're helping or not. If you have some notion of positive controls. So in the case of a gender study, you don't know necessarily for sure which genes are going to be differentially expressed between men and women, but you have a pretty good guess that at least a lot of them are going to come from the X or Y chromosome. So what I can do is I can treat genes from the X or Y chromosome as positive controls. Once I rank my genes, I can go through and I can count, for example, how many of the genes from the X or Y chromosome show up in the top 10 once I rank them. And I see that, for example, 9 do. Or how many in the top 50, and I see that 21 do. So looking at a plot like this can help us give us a sense of whether or not we are helping or hurting. There's this line here. This shows us what this plot would have looked like if I had just assigned p-values at random to everything. Okay, so we're clearly doing a lot better. Okay, I'm going to skip over these other plots. I want to. Oh, this is just to highlight, again, have we helped? This is what an unadjusted limit analysis would have looked like. The p-value histogram is messed up. We don't find as many positive controls. Okay, I'll try to keep it to just an extra 5 minutes, but I want to show you some of the global adjustments. I'm going to skip over the RUV1 stuff. I'm going to go straight to the RUV3 stuff. RUV3 also requires some notion of replicates. M is going to be the mapping matrix that describes the replicate structure. So it takes our observed expression data, it takes a matrix that describes the replicate structure, it takes our negative controls, and then some other parameters. What I mean by the mapping matrix, this is a matrix of dummy variables where for row I and j of this matrix, it's 1 if observation 1 is in replicate set j, and it's 0 otherwise. So basically, each column of this mapping matrix represents a set of replicates, and the rows of that column that are 1 tell you which of the microarrays are part of that set of replicates. Okay, and of course, it's certainly the case that some what we'll refer to as replicate sets are really just a single array. So in other words, they can be singletons. Again, the key assumption when we're using RUV3 is that any variation within a replicate set is assumed more or less by definition to be unwanted. Okay, there's a function here that helps you create these mapping matrices. I'll skip over that. It's in the documentation. I'll skip over that. It's in the documentation, but I want to at least show some results here. And in this first example, I'm going to have as my negative controls, I'm going to have the spike-ins, and as my replicates, I'm going to have the technical replicates. So the same tissue samples, but at the 3 different labs. As a reminder, this is what the data looked like before normalizing, and here is what my mapping matrix looks like. So again, these 3 samples are all the same. These 3 samples are all replicates. These 3 samples are all replicates, and so on. And then here is the normalized version of the data using RUV3. Okay. I'm going to skip over this. I want to get to example 2. In example 2, I'm going to do essentially what I just did, except this time when I make the PC plot, I'm going to make a PC plot of only the genes from the X or Y chromosome. And I want you to think just for a second. So now I'm taking just genes from the X or Y chromosome. What do you expect that we will see before adjustment and after adjustment? So before adjustment, it actually looks pretty much exactly the same. Again, these are genes just from the X or Y chromosome. But still, by far the biggest signal in the data is the lab effect. I've changed the graphic parameters here a little bit so that now I can look at the difference between men and women. And there is no sign of the gender effect in here. Now I'm going to adjust. interestingly, after this adjustment, now the biggest source of variation is the brain region. Okay, so again, this is just the genes from the XY chromosome, but even there, the biggest source of variation is the brain region. Okay, now this next example is going to help make the point that I was trying to make earlier about how the negative controls and the replicates can help define which variation is wanted and which variation is unwanted. So what I'm going to do now is I'm going to use as my negative controls housekeeping genes, and I'm going to use as replicates all observations from a single patient. So for each patient, there's the 3 different tissue samples from the 3 different brain regions, and each of those are sent to the they're sent to 3 labs. So for each patient, there's 9 microarrays. I'm going to use all of them as my notion of a replicate. And again, for the negative controls, I'm using housekeeping genes. So now the mapping matrix looks like this. These first 9 are all from patient 1, the second 9 are all from patient 2, and so on. And now, after I adjust this way, the biggest source of variation is the difference between men and women. Okay, so by changing my notion of replicate and by changing my notion of negative control, I have changed what implicitly I am calling wanted and unwanted variation. I now get a very different result. I want to pause and linger on this just for a second more. I want to point out that what I just did, there's more going on here than simply just, in some sense, regressing out brain region. I've done a little bit more than that. So just as a comparison, here I am quite literally regressing out brain region. So I do the adjustment that I had already done using the spike-in controls and just the technical replicates, and then I explicitly regress out brain region. And when I do that, I get a different looking thing. I do not see the gender effect. Partly that's because this is driven by this extreme outlier, but even if after I remove that outlier, I still do not see gender coming up as the main effect. If I skip forward to now, I'm looking at the 3rd and 4th principal components. It's only by the time I get to the 3rd and 4th principal components that I'm beginning to see this gender effect. So by using this other notion of replicates and this other notion of negative controls, so using the housekeeping genes and biological replicates, I've come up with a stronger adjustment. I've adjusted for not just brain region, but many other sources of biological unwanted variation. And another important difference between what I just did and simply regressing out brain region that actually isn't relevant to this example because we have a nice balanced design. But you can imagine that if I had a design that was not balanced, if I just naively regressed out brain region, but brain region was itself correlated with other biology, I might be wiping out that other biology as well. With the RUV3, however, even if you have an imbalanced design, you won't be wiping out biology of interest, even if it's correlated with your unwanted factors. I have one final example. Here I'm going to use yet another different notion of replicates. I'm going to treat all of the samples from the same brain region as a replicate. So in this case, my mapping matrix looks like this. I've got one set of replicates is the anterior cingulate cortex, one is the cerebellum, and one is the dorsolateral prefrontal cortex. When I do that, okay, so not surprisingly, the brain regions pop right out. But that shouldn't be surprising. I basically fed information about the brain regions into the algorithm. What I'm going to do here, though, is I'm going to do what I call bursting. I'm going to burst the cerebellum and the dorsolateral prefrontal cortex, meaning I'm going to treat everything that's cerebellum and anything that's dorsolateral prefrontal cortex. I'm going to treat all of those as singletons. I'm not going to treat any of them as replicates of each other. So, in fact, what I'm going to have is a replicate structure where I'm only going to treat samples from the AC cortex as replicates. So to see this visually, this is what my replicate structure is going to look like. I'm going to call everything from the anterior cingulate cortex a replicate, and then everything else is going to be treated as a singleton. When I do this, uh-oh, where did it go? Oh, shoot. What I can do, well, that's disappointing. Okay, well, you can go back on Docker and you can rerun it yourself. But I'll tell you what it would have looked like. What it would have looked like is that the anterior cingulate cortex samples, those are the ones that I treated as replicates, they would have all been very, very tightly clustered. And that's because I basically told the algorithm that those are replicates, and it removed all the variation within that replicate set. But then also, you would have gotten still a very nice separation between the cerebellum and the dorsolateral prefrontal cortex. Things that I did not explicitly tell the algorithm were replicates, but they do cluster very nicely. What I want to say about this, one is that bursting is useful for validating adjustment. So, for example, I only tell the algorithm that the AC cortex are replicates, but then I see very nice clustering between the other two groups. So I know that I've done a good job. But even more exciting, I think, is what I think that this says that I might be able to do in a particular example that I'm pretty excited about pursuing. And the idea would be this. Say that I want to do some sort of cluster analysis and I want to discover disease subtypes. And so now very often when you do a cluster analysis to try and discover disease subtypes, you find clusters, but then very often it's kind of an open question of these clusters that I found, do they actually have anything to do with the disease? So there might clearly get some clusters, but are they disease relevant clusters? And what I'm hopeful that might be able to be done using this RUV framework is to do something like this. To say I'm going to get myself some healthy controls, and I'm going to treat all of the healthy controls as biological replicates. And by treating all of these healthy controls as biological replicates, I will be capturing all of what might be considered ordinary biological variation. I can then adjust for that ordinary biological variation, and then with any luck, afterwards what will be left is only disease-related information. And so when I look at my clusters, I'll have at least some extra reason to believe that these clusters that I'm looking at are actually related to disease. Okay, so I know that I'm already over.
Yeah, we should probably wrap up.
I will stop there. I'll just point out that if you do go on the Docker, there's a Shiny app, and you can use it. All right, good. Thanks.
I might suggest that we take questions offline too, since we're sort of a little
Yeah,
over time.
makes sense.
Thanks.
Thank you.